Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process by great saint Swami Vivekananda, who says the secret of life is not enjoyment, but education through experience. Unfortunately, the education being imparted in India today is devoid of much experience. So, let us now recall what we learned in the last lecture. We basically started discussion on types of injectors which are being used in rocket engines. All types of injectors can be broadly divided into two categories. One is impinging injector or atomizer, other is non-impinging atomizers. If you recall, we discussed about three types of non-impinging injectors. Those are basically shower injector and coaxial injector and swivel injectors, and those are being used generally for non-hypergolic propellant. An impinging type of atomizer can be used for both hypergolic and non-hypergolic propellants. And doublet impinger, there are various kinds, but we discuss only some of them. Doublet impinging injectors, triplet injectors, then splash kind of thing, unlike injectors. Generally, the unlike impinging injectors are used for hypergolic propellant, or the like impinging injectors are being used for the hypergolic propellants. So, later on we also looked at a general analysis for an atomizer considering a simple orifice and derive expression for mass flow rate by considering the Bernoulli's equation, and then of course, we include the real effect by considering the discharge coefficient. And in the end we really derived an expression for oxidizer to fuel mass flow rate ratio that we label as MR, sometimes we call it as a mass flow rate ratio, which is expressed in this equation, that is NOx CDOx AOx root over 2 rho x delta P OX divided by NF CDF, and this CD basically discharge coefficient with respect to fuel, AF is the cross sectional area of fuel, and root over of 2 rho f delta P f. Keep in mind that this can be utilized in various ways. For example, if you want to find out diameter of the oxidizer and the fuel, you need to know the MR, you need to know the discharge coefficient, also the NOx, that is the number of the fuel elements or the oxidizer element, number of oxidizer elements in the atomizers, and similarly NF is the number of fuel orifices in the injector. So, therefore, we can utilize in various ways. We will take an example to illustrate how this expression can be utilized. Let us take an example to illustrate how we can use the relationship for solving a problem. In this example, we are considering a liquid propellant rocket engine is used to develop a thrust of 12 kilonewton with characteristics velocity of 2050 meter per second at chamber pressure of 6.8 megapascal and MR of 1.6. If its thrust coefficient happens to be 1.65, determine the mass flow rate of oxidizer and fuel. An injection system with 10 orifices is used with injection pressure drop of 1 megapascal and discharge coefficient of 0.76 for both oxidizer and fuel streams. And by considering the density of fuel and density of oxidizer to be 860 and 1100 kg per meter cube, determine diameter of injection holes. This is a very simplified problems which can help you to appreciate the analysis which we had done earlier and how we can use that analysis for designing the rocket injection system. So, let us look at basically what are the quantities are given. In this case, like if you look at, it is the thrust which is given, that is F 12 kilonewton, and the characteristics velocity C star 2050 meter per second, chamber pressure 6.8 megapascal, and the mass ratio, this is basically mass flow rate of oxidizer divided by mass flow rate of fuel, is equal to 1.6, and keep in mind that this mass ratio is different than what we had used in flight mechanics lectures. And the thrust coefficient Cf is 1.65, and also the orifices, number of orifices for both the fuel and oxidizer is basically 10, which in real situation it need not to be the same. And with injection pressure drop delta P oxidizer delta P fuel is equal to 1.5 megapascal, and discharge coefficient is 0.76 for both fuel and oxidizer streams, and density of the fuel is 860 kg per meter cube and rho of oxidizer 1100 kg per meter cube. And we will have to determine basically the mass flow rate of oxidizer, mass flow rate of fuel, and the diameter of oxidizer, diameter of fuel. So, let us look at how we can solve this problem. For this to find out, because M r is given, that is the ratio of m dot oxidizer m dot f. So, what we need to find out, what is the total propellant flow rate, that is m dot p is nothing but your m dot oxidizer plus m dot fuel. That we can find out very easily, right, by knowing we can determine m dot p as we know F divided by ISP and G naught. ISP is not given, G naught we know, F we know, but we know ISP, I can find out Cf C star by G naught. So, if you look at, like, I can get this very easily, that is Cf is given, that is 1.65, and C star is given 2050 divided by 9.81, and that is nothing but here 344.8 second. So, if I substitute these values over here, I will get 12 kilonewtons, that is 12 into 10 power to 3 divided by 9.81 into 344.8 is equal to 3.5 0.47 kg per second, because this is a mass flow rate. And of course, we know this is, I can say this is the equation 1, and we know that MR. So, I can express that by using equation 1 and also using this relationship MR, I can find out that we know that m dot oxidizer is nothing but your m r divided by 1 by m r into m dot p. If I look at that, this is m r is basically your 1.6 divided by 1 plus 1.6 into m dot p 3.547, and that is equal to 2.18 kg per second. And then I can very easily find out that is m dot fuel will be basically 1.365, because I know that m dot p and I know m dot oxidizer. Therefore, by using equation 1 I can get very easily. And now we will have to find out basically the diameter of oxidizer, but we know m dot oxidizer is nothing but number of oxidizer pore orifices, C d of oxidizer and A of oxidizer, and root over 2 rho of oxidizer delta P oxidizer. If you look at in this expression, except A of oxidizer, everything are given. So, therefore, I can from this expression I can find out d oxidizer is nothing but your 4 by pi m dot oxidizer divided by n of oxidizer, C d of oxidizer, root over 2 rho of oxidizer delta P oxidizer. So, root over of this, and if I substitute these values, I can get basically all are given 4 by pi m dot oxidizer is nothing but your 3.547 divided by 10 into C d of oxidizer 0.76 root over 2 into rho of oxidizer is 1100 kg per meter cube into the pressure. Pressure is basically drop across the oxidizer is 1.5 megapascal, 1.5 into 10 power to the 6, 2.52 mm. This is basically millimeter. And similarly, we can determine diameter of the fuel as 4 by pi m dot fuel n of fuel C d of fuel root over 2 rho of fuel delta P across the fuel stream. So, if I substitute these values 4 by pi m dot f 1.365 divided by 10 into 0.76 root over 2 into 860 into 1.5 10 power to 6 is equal to, you will get 2.12 mm millimeter. So, now we could manage to really determine the diameter of orifices by using this expression, which is very simple and one can do that very easily. In real problems, of course, there will be several things which need not to be same for the both the oxidizer and fuel. So, also the C d values will be different for oxidizer and fuel, and so also the pressure drop across the fuel and oxidizer will be different. So, let us now look at how to analyze the impinging atomizer. We are considering the generic atomizers. There are two atomizers. In this diagram, we are considering two streams, that is the fuel stream, this is your fuel stream and this is your oxidizer stream are being impinging, and this fuel stream is passing through this orifice with a certain area. Let us say this is your AF and this area is a oxidizer. It is impinging with VF, making an angle alpha f with respect to x direction. If you consider this is your x direction and this is your y direction, and in the similar way the oxidizer is exited from this orifice AOX with a velocity of VOX and mass flow rate of m dot OX, making an angle alpha OX with respect to the axis. And keep in mind that, and this is your impinging point, and after getting impinging we are assuming total mass flow rate is basically moving with the same total mass flow rate and with certain mean velocities. And keep in mind that this alpha x, this angle is nothing but beta, which is alpha f plus alpha O x. So, and when this is impinging from the impinging point, the total mass flow rate is moving with the same velocity, mean velocity, that is V m. This is your mean velocity after impinging point, and this is the total mass flow rate of oxidizer and mass flow rate of fuel. Keep in mind that that means mass is conserved, but in real situation it is not that two jet of the liquid will be impinging and it will be moving with that. Rather it will be splashed out, some of the liquid will be disintegrated from the bulk liquid and maybe some portion will be moving a certain velocity. But this is the assumption we are making for simplifying the analysis. And let us make another assumption, that is the momentum impinging jet is same before and after impact. That means momentum is conserved, and so also the mass is conserved, as we have assumed that the after impingement both the fuel and oxidizer will be moving with the same mean velocity and total mass flow rate of the oxidizer and fuel, which will not be really true in real situation. So, that means it is saying that as if it is elastic collisions, and so that the momentum is conserved, when real situation it is not the case. So, for that what we will do, let us now resolve these components of the momentum, that is, as I told, it is in the x direction, this is your x direction, this is your y direction. If I resolve this momentum along with this direction in the x direction, this will be basically m of f and v f, right, and cos alpha f, and in this case in this direction it will be m dot f v f sin alpha f, and the similar way in this direction this will be negative sign. However, this will be oxidizer V oxidizer sin alpha of oxidizer. So, therefore, if we resolve this component and write it down, we will see that y momentum will be m dot f v f sin alpha, this is in the positive y direction, therefore, it will be, whereas the oxidizer will be having negative direction, therefore, the minus sign m dot oxidizer VO oxidizer sin alpha, and this net momentum will be conserved in the y direction, therefore, is equal to the after impingement, that is the total mass flow rate of oxidizer and fuel into V m sin theta. So, if you look at this direction, it will be m dot oxidizer plus m dot F momentum V m sin theta, and in this direction this will be fuel and V m cos theta. So, let us say this is your equation 1, and similarly we can write down x momentum as m dot O x V O x cos alpha O x plus m dot F V f cos alpha is equal to m dot O x plus m dot F V m cos theta. Keep in mind that these are all in the along with the x direction, therefore, it is positive. Let us say this is equation 2. Now, if I divide equation 1 by equation 2, you can get this very easily, like if we do this portion, if I divide this equation, so you will find that this will cancel it out, okay, and this can be equal to basically equal to this. So, then you will get an expression that is tan theta is equal to this portion, that is m f b f sin alpha minus m dot O x v O x sin alpha O x divided by m dot v f cos alpha plus m dot O x v O x cos alpha x. And keep in mind, generally this theta is should be 0 for better atomization or better performance. So, if this is 0, let us say this is 0, then this term will be basically multiplied by 0 become 0. Therefore, you will get an expression that is this expression will equal to 0, and that is here it is written. So, and I can take this expression as I can rewrite down m dot f v f sin alpha f is equal to m dot O x v O x sin alpha O x. So, if I will divide this one here m dot O x and v O x v O x, and you will see that this will cancel it out, and this is you know what it is, this is basically, and so therefore, we can write down this as m dot f m O x v f sin alpha x, this is the left hand side portion, is equal to, we can write down instead of this v f, we can write down the expression for from the previously derived expression for velocity of the fluid, that is C d and root over 2 delta p divided by rho. And you will find that this is nothing but your sin alpha x, but we know that beta, that is alpha O x, is beta minus alpha f. So, therefore, I can write down here this portion, instead of alpha x I can write down here. So, when you expand the sin beta minus alpha f, I will get sin beta cos alpha minus cos beta sin alpha. And what I will do, I will take, if you look at this alpha f is there in the left hand side. So, I can take this portion to this expression here plus this portion, and then I can separate it out, and I can have expression that this is your this term and these terms, and then if you look at cos beta, nothing but sin alpha is equal to sin beta cos alpha f. Now, I can put this thing over here, divide by cos alpha f, I can divide by cos alpha f, this will cancel to 1. So, I will get basically an expression for tan alpha or the simply alpha tan inverse of this sin beta divided by this expression. Keep in mind that if I know this beta, which generally people use 90 degree, right, for the better performances, right, of atomization. So, therefore, if I know this and if I can choose these CD values and I know the MR other things, I can get this alpha f very easily. Once I get this alpha f, I can get the alpha oxidizer as well. So, this is a simple expression which has given, so that you can do analysis and find and use it for designing atomizer for impinging one. We will stop over here and we will discuss in the next lecture about the injector distributor. Thank you very much.